time. So this is the first problem. Initially, I will solve the first problem and then I will start with the third one. And depending on the time, if we have time, then we will start with the second problem, okay? So the first question, guys, look carefully. This is the schematic here. We have the water tank or water reservoir here. This is our free surface, okay? So at free surface means the pressure is atmospheric pressure here. We have the pumping system like this. The pipe is kind of inclined and it makes a 30-degree angle here. So you will see it makes a 30-degree angle here. We have the pump at these positions. The diameter of this pipe, it was constant throughout up to this, and then it becomes narrow. Let's say this is the nozzle. This elevations, the height S, it is equal given 30 meter. So that means this is the total elevations from this pipe inlet to the exit of the pipe, okay? So that's given 30 meter. This has, it is given 10 meter. So that means you can say the water head, it is 10 meter. And the angle 30 I already mentioned. The diameter here is 160 millimeter, 160 millimeter. And the diameter here is, it is 80 millimeter. The flow rate actually for this problem, you'll see the flow rate, it is given 120 liter per second. And the water temperature is 20 degrees centigrade. It says, you just assume that this is the ideal flow. So if we assume this is the ideal flow, then we will not consider any the heat loss here. So we can neglect the heat loss for ideal flow. So, okay, that's the thing. We need to calculate two things here. One is the distance, the maximum distance x, when cavitation is about to appear at the pump inlet. So this is the pump. We need to calculate this distance from here to here. So what will be this distance when the cavitation will start? So we need to recall our memory now. When cavitation starts, what's the pressure over there? So we know cavitation means just the formation of the droplets, and these droplets apply the pressure on the water surface. So this is the vapor pressure. We discussed it a couple of weeks back, I think, when we did some discussion on the pressure measurements. So at this pump, when you have the pump and if the cavitation starts over there, the pressure at this pump, it will be the vapor pressure. Okay, so it will be the vapor pressure. And we'll see what is the temperature, 20 degrees centigrade given. So the vapor pressure is at 20 degrees centigrade, it's constant to 340 Pascal. Anyways, so to solve these questions, what we know, guys, we know the height, it is equal 10 meter, okay? And we know the diameter, the pipe diameter, okay? We can say the DP, that means the pipe diameter is 160 millimeter. The nozzle, the exit diameter, the exit of the pipe is 80 millimeter. The S, that's the elevation, is 30 meter. Theta is 30 degree. And the barometric pressure at this problem, you will see it is given, the barometric pressure is 101.3 kPa. So that's given. So this is all about the informations we have. Now we will calculate this height. Okay, before going to solve this problem, we know this water head, we know this head, these elevations. Do we know what's the head, like what's the elevations of the pump? So pump is located here. You just see the pump location is here. Do we know this height? We don't know. We don't know this height. So how we can calculate that? You see, this pump, this is the pipe, this is the pump, it makes a 30-degree angle like this. So can I just draw it like this? So if this is the pump locations, so let's say this is the pump height. It makes 30-degree angle here. So if you just closely look here, the distance from here to here, this is x. Can I say this is also x? We can. So now I will say, okay, this is actually x, because we just extract this triangle here. If this is 30, if I say this is A, this is B, this is C, I can say this is x tan 30. If you ask me how you can tell that, we know tan theta, it is equal the vertical distance over the perpendicular distance. That's the trigonometric formula of the tan theta. So that means BC over AC. So it is, we can say tan theta equal BC over x, because AC equal x. Or in other words, we can say BC equal x tan theta. You understand what I mean? So that's actually how I write it is x tan theta 30. So now I can say it is x tan 30. So I will just spend a little bit time here. If you are still drawing this figure, just finish it. So we said the elevation for the water, it is 10. From the inlet pipe to the exit pipe elevation is 30, and the pump elevation we got x tan 30. And if you ask me that why you need that, you see the first part of the question is we need to calculate the x, the maximum distance. So it is actually when we will use the Bernoulli equations between this point, then we need that. So I will explain it, don't worry. So if you have done with the writings, then I will just change the screen. I can see some of you still writing. So let me check how many people we have online. We have 8 people, that means 7. So guys, do you have any questions like how we got it is x tan 30?
No, clear.
Clear,
So
good.
clear.
All right. So this question, you will see, it is just the, we need to use all the basics, whatever we have learned so far. In this question, we will use everything, like the Bernoulli equations, the energy equations, the momentum principles. And later on, when we will solve the second question, then you will see, we'll use the fluid statics pressure measurement knowledge. So this lecture is actually, the summary of whatever we have done so far for these subjects. And it is really important. You will get at least 10 marks from these tutorials in the final exam. Anyways, so let me change the screen now. So we have got, this height is x tan 30. Now, if I say this is point A, okay, this pump location we say I, and the exit of the pump, it is E. Okay, I just define this way. Now, if I use the Bernoulli equations, here, then Bernoulli equations between A and I. Try to understand, I'm just applying the Bernoulli equation between A and I because we are looking for this x. So we're just applying this. So it is PA rho G BA square 2G ZA, it is equal PI rho G VI square 2G and ZI. Right. So if you know, guys, here what is PA? PA is the barometric pressure is given in the questions, which is 101,300 Pascal. It is given in the questions. You look, it is given on 013 kPa, the barometric pressure. Okay. So we know that PI is actually the vapor pressure. That means the pressure at the pump when cavitation starts. So this vapor pressure is 2340 Pascal. And Z1, can you tell me what is Z1 here? So let's say not Z1, ZI, it should be ZI. X1030, yes. It's X1030. What is ZA? It's 10. It's 10. This is 10. 10 meter. What is VI? And what is VA? The fluid is here. At this point A, velocity is VA. So VA is 0, isn't it? VA, this is 0. VA, it is 0. But do we know the VI? We don't know. We don't know. But what we know is, we know the flow rate. Okay? The pump flow rate. Okay, so what we need to do here is, the flow rate is given. Flow rate is 120 liters per second. If we want to calculate the velocity, then we can say, okay, the flow rate over the area, isn't it? It's flow rate over area. So flow rate is given 120 liters per second, and the area pi d squared over 4. Because this is a circular pipe, okay? So it should be 0.120 meter cube per second when we will convert it into meter cube per second, from liter to meter cube per second. And this is pi. What is the diameter, guys? For this pipe, you will see, just a second. Yep. So you will see the diameter is given. The diameter is given here, 160, and this outlet diameter is 80. So what we can write down is the diameter is 0.16 square over 4. So we'll get this flow rate is, the velocity is 5.97. So this is the velocity. That's the pump inlet velocity, 5.97 meter per second. So we have got all these values. Now, what we will do is we will substitute all these values here. So do that. PA is 10130. The density is 1000. Gravity is 9.8. I'm not writing the units because if I try to write the unit, it will be so messy. So it's pretty straightforward calculation. So I'm not writing the units here. BA, as the velocity is 0, so we can cancel it out. This is 0 velocity. ZA, it is 10. PI is the vapor pressure, we already mentioned. Density is 1000. Gravity is 9.8. BI 5.97 square. It is 2.98 is the gravity. And the ZI is given X 1030. X 1030. So if you have a close look, guys, here, all the values we know except the X here. So in these equations, we have one equation, one unknown. So if we now use the calculator, if we solve it for X, it will be 13.7 meter. So we just need to use the calculators. I'm not just expanding it, but I'm just writing the final value. So it's 31.7 meters. So that's the maximum, the distance that we need to calculate. That's the first part of this problem. So I believe you understand. Do you guys have any confusions with this? I think this is straightforward thing, right? So this is the first part. And the second part of the problem, it asks about, we need to calculate the pump power. Like when we are using this pumping system, what's the pump power for this given data, like whatever it's given, what's the pump power? So I'll move to the next phase. Anyone is still writing? No. So then I'll move to the next phase. We need to calculate the pump power. So guys, pump power, we know the formula. It is actually the density, gravity, its density, the gravity, you can say the flow rates, and the pump heads. Okay, so that's the formula, like how we can calculate the pump powers. So we need density, gravity, we need the flow rates, and we need the pump heads. Pump heads is unknown, and rest of the information we know. Like the density, gravity, and the flow rate, everything we know, but we don't know the pump heads. So if we actually want to calculate the pumping heads or the heads, how we can do that? Can you tell me which principle or which equations we need to use to get these pump heads? Anyone? To get these pump heads, energy equations? Can we use the energy equations?
Yes.
Yeah, we can use the energy equations here, and we can, solve it. So let's just a second. Let me move it a bit more. Yeah. So from when we're talking about the pump powers, this is our point A. The pump is point I and the exit is point E. If we apply the energy equations between point A and E. So from the energy equations we know PA rho G, VA square 2G, ZA, and this is the pump heads. Then PE rho G, VE square 2G, ZE plus the head loss. You see, this is the modified version of the Bernoulli equations. Now, as we're solving a problem, this is the ideal flow, it's given in the questions. So that means we have got no head loss. So that means the head loss, this is 0. We have the water reservoir here. So the pressure, it is atmospheric pressure. This pump, it is discharging water to the atmosphere. So the pressure here, this is the atmospheric pressure, right? So can I cancel out this pressure and this pressure? Because they both are atmospheric pressure. Now, this is the water reservoir, water tank. Fluid is at rest. At this surface here, the water velocity is 0, isn't it? So pump is just pumping the waters, but here initially the velocity is 0 for the water, so we can say this is 0. Okay, the VA, this is 0. So now we have these expressions. It is we can say, if we simplify this, we can say the pump heads, this is equal VE square 2G plus ZE minus ZA. This is the final, the energy equations now becomes like this. We know ZE. What is ZE, guys? This is this height. It is 30 meters. We know ZA. This is actually H equal 10. But what we don't know, is VE, the velocity at the exit of the nozzle, okay? So we now need the VE. That means the velocity at the exit of the pipe. And now the question is how we can get it. Anyone can answer this question. We need the velocity at the outlet of the pipe here at this exit point. So we know the velocity, the pump inlet velocity. Can you use the momentum principles, mass conservation principles? Mass conservation principle means the mass coming through the inlet and the equal amount of mass going to the outlets. So then we will apply this formula here. As we know the velocity at these sections, so we can calculate the velocity here as well. So let's say from the mass conservation principle, we're applying this at point I and point E. So we can say the velocity I into area and the velocity E into area, they're same, because we know flow rate, it is equal velocity into area. You just look here, the flow rate equal velocity into area. So we said the velocity, the flow rate at the the pump inlet will be equal to the flow rate at the exit of the pipe. So that's the mass conservation principle. Okay, and it is all of the other thing. You can say that the continuity equations, and you already know it. We solved some problems all there like this. So now I can say it is VI phi di square over 4. This is circular pipe, okay? So pi di square, and here VE pi over 4. This is DE square. As we're talking about the exit, so we said it is E. Now can I cancel out this pi over 4? We can. Then we can write VE. This is equal, if we simplify this, it will be, it will be, VI DI square over DE square. So velocity VI, we know this is 5.97. DI, the diameter, is 160 millimeter, right? 160 millimeter, and that one is 80. Okay, so that means 0.16 square, and this is 0.08 square. So we'll get this velocity VE equal 23.88 meter per second. So this is VE, the exit velocity is 23.88 meter per second. So that's the exit velocity. Now guys, if we substitute this exit velocity here, we will easily get the pump heads. Okay, I will upload. You don't need to take the photo. I'll upload the clear solutions, okay? So I have the the work solution. So I already uploaded it. Yeah, don't worry. And this work solutions, like what I'm doing now, I'll try to scan it. So I can't actually save it. I'm using some apps. It's called Keynote. So I cannot actually save it, whatever I'm doing. If I just change the screen, everything will go. So I had another session this morning. So I have some like handwritten things. So I'll upload that one, okay? Yeah. But if you can't understand, just don't hesitate to ask me questions. So we have got the VE equal 23.88. So that's the exit velocity. Also, I'm recording for this session. I will upload the recordings. Okay, I usually don't upload the tutorials recording because we have 6-7 tutors. So different tutors, they follow different style. So if I upload, then it may confuse other students. But for this one, I will usually upload it because it's one of the complex tutorials we are doing in this semester. So you will see when I will solve the third problem, I can say that's the most complex tutorial we're doing today. So we have VE, this is equal 23.88 meter per second. Right, so now simply substitute the value here, the pump head. So we know the pump head, this is equal VE square over 2G. Let me check it here. Plus JD minus ZA. ZE minus ZA. So this is 2388 square into 2.98. The ZE is 30. ZA is 10 meter. So if we calculate it, guys, we'll get the pump head is 49.1 meter. So this is the pump head. And now we have done with these problems. We know the pump power. This is equal density, gravity, flow rate, and the pump heads. So the density is 1000, gravity is 9.8, and the flow rate is, can anyone help me? What is the flow rate? Point on to O, right? Yeah. 0.120 meter cube per second. And the pump heads is 39.1. So we'll get the pumping power is 57760 watt. So this is the solution.